When I say that the universe does not respond, I mean something very specific. I mean that when we look out with our telescopes, when we send signals, when we wait for a reply, the cosmos behaves exactly as physics predicts, and not at all as if it is aware of us. The universe follows rules. Those rules include gravity, quantum mechanics, relativity, and the strange ingredients we call dark matter and dark energy. None of those rules include any mechanism for the universe to notice that we are here and then change its behavior. That is not a philosophical claim. It is a scientific one, built from observation, experiment, and a lot of careful checking. To understand why the universe feels silent and unresponsive, I need to talk about how it actually behaves. The key ideas are spacetime, gravity, dark matter, dark energy, and cosmic expansion. These are not decorations on top of some more personal or reactive universe. They are the structure itself. When we say space-time, we mean that space and time are not separate, rigid backgrounds. They form a single four-dimensional fabric. Matter and energy tell this fabric how to curve. Curved space-time tells matter and light how to move. That is general relativity, Einstein's theory of gravity, and it has passed every test we have thrown at it so far. In this picture, gravity is not a force that reaches out like a hand. It is geometry. A planet orbits a star because the star curves space-time. The planet follows the straightest possible path in that curved geometry. We call that path a geodesic. The planet is not asking for permission. The star is not choosing to pull. Both are simply following the rules of the space-time they are in. When we talk about the universe not responding, we are seeing this same pattern at every scale. The universe evolves according to physical laws that do not include intent, purpose, or reaction to our presence. How do we know that space-time is curved and that gravity works this way? We test it. We measure how starlight bends around the sun during an eclipse. We watch how the orbit of Mercury shifts over time. We track the timing of pulsars. We detect gravitational waves from colliding black holes. Each of these experiments checks a precise prediction of general relativity. So far, the theory holds. That gives us confidence that when we model the universe as a whole using these equations, we are capturing something real about how it behaves. Now let me connect this to the large-scale universe. When we look at galaxies, galaxy clusters, and the cosmic web, we see patterns that come from gravity acting over billions of years. We also see something else. The visible matter, the stuff that shines, is not enough to explain what we observe. Galaxies rotate too fast, clusters hold together too strongly, light bends too much as it passes near massive structures. If we add up all the stars, gas, and dust, the gravity is too weak. The motions and the bending of light tell us more mass must be there. We call that missing mass dark matter. Dark does not mean mystical. It just means it does not emit, absorb, or reflect light in any way we can currently detect. It interacts mainly through gravity. We infer its presence because of its gravitational effects. For example, when we measure the rotation curve of a spiral galaxy, we find that stars far from the center move almost as fast as stars closer in. If only visible matter were there, the outer stars should move more slowly, like planets in our solar system. Instead, their speeds stay flat. The simplest explanation is that the galaxy sits inside a large halo of unseen mass. That halo is dark matter. We also see dark matter in gravitational lensing. Light from distant galaxies passes near massive clusters on its way to us. The cluster's mass curves space-time and bends the light. We can reconstruct how much mass is there by how the background galaxies are distorted. When we do this, the mass we infer is again much larger than what we see in stars and gas. Different methods, same conclusion. There is a lot of matter that does not shine. That is dark matter. On even larger scales, we can map the distribution of galaxies across hundreds of millions of light years. We see a cosmic web, filaments, nodes, and voids. Simulations of structure formation that include dark matter reproduce this web very well. If we remove dark matter from the simulations, the structures do not match the real universe. So dark matter is not just a patch for one problem. It consistently explains many independent observations. Now, dark matter is part of why the universe does not respond. It is there shaping the evolution of galaxies and clusters, but it does not care about light, chemistry, or biology. It does not react to our signals. It does not absorb our messages or answer them back. It simply follows the gravitational field. It deepens potential wells. It seeds structure. It forms the backbone of the cosmic web. It behaves the same way whether or not life ever appears in the universe. What about dark energy? Dark energy is even more directly tied to the universe's apparent indifference. In the late 1990s, astronomers studying distant Type 1a supernovae expected to find that the expansion of the universe was slowing down. Gravity, after all, pulls things together. If the universe started expanding in the Big Bang, that expansion should gradually decelerate as matter pulls on matter. But that is not what the data showed. The supernovae were dimmer than expected. They were farther away than they should have been in a decelerating universe. The only consistent explanation was that the expansion of the universe is accelerating. To describe this acceleration, we introduced dark energy. Again, the word dark means unknown in detail, not magical. In the simplest model, dark energy is a constant energy density built into space itself. As the universe expands and new space appears, the total amount of dark energy increases because there is more space to contain it. This energy has a strange property. Its pressure is negative. In general relativity, not only energy density, but also pressure contributes to gravity. Negative pressure leads to a repulsive effect on large scales. It does not push things apart like an explosion. Instead, it causes the scale factor of the universe, the measure of cosmic distances, to accelerate over time. How do we know dark energy is real and not just a mistake in one dataset? We cross-check. We see its imprint in the cosmic microwave background, the afterglow of the Big Bang. Tiny fluctuations in that background radiation, mapped by satellites like WMAP and Planck, tell us about the contents and geometry of the early universe. The pattern of those fluctuations points to a universe that is spatially close to flat and filled with about 5% normal matter, about 25% dark matter, and about 70% dark energy. Large-scale galaxy surveys measure how structure grows over time. The rate of growth is slower than it would be in a universe without dark energy because the accelerated expansion pulls matter apart faster. Baryon acoustic oscillations, subtle ripples in the distribution of galaxies also support this picture. Different probes, different epochs, same conclusion. Some form of dark energy is driving cosmic acceleration. So we arrive at a striking summary. The universe is about 5% ordinary matter, 25% dark matter, and 70% dark energy. The part that makes stars, planets, and people is a small fraction. The rest shapes the overall evolution of spacetime, but does not interact with us in any direct communicative way. It does not encode a message. It does not change when we look at it. It does not respond. Now, I want to be clear about what we know and what we do not know. For dark matter, we have strong evidence that it exists and that it behaves like a cold, collisionless fluid on large scales. But we do not yet know what particle or particles make it up. Candidates include weakly interacting massive particles, axions, sterile neutrinos, and others. Experiments deep underground, at particle colliders and in space, are trying to detect dark matter directly or produce it. So far, there is no confirmed detection. That is an open problem. For dark energy, our ignorance is even deeper. The simplest model is a cosmological constant, a fixed energy density of the vacuum. That fits current data well. But we do not know why the vacuum energy has the value it does. Quantum field theory suggests it should be enormous, many orders of magnitude larger than what we infer from cosmology. The fact that it is small but non-zero is a major puzzle. There are alternative ideas, like slowly rolling scalar fields, sometimes called quintessence, or modifications of general relativity on large scales. At the moment, observations are consistent with a cosmological constant, but the error bars still allow some room for more complex behavior. So dark energy is a name for a measured effect, not yet a complete explanation. Now, how does all this tie back to the idea that the universe does not respond? In physics, we describe the universe with equations that are local and causal. The behavior of a system at a point in spacetime depends on the conditions in its past light cone, not on distant observers or their questions. If I point a radio telescope at a galaxy a billion light years away and send a signal, that signal travels at the speed of light through spacetime. It carries energy. It can, in principle, push on particles or heat dust when it arrives. But the large-scale expansion of the universe does not adjust because I decided to send that signal. The value of dark energy does not change. The distribution of dark matter halos does not rearrange. Our actions are too small and too local to affect the global behavior of the cosmos. Even quantum mechanics, which is often described in mysterious terms, does not rescue the idea of a responsive universe in the sense of cosmic awareness. Quantum systems are sensitive to measurement, but that sensitivity is local and governed by precise mathematical rules. When we measure a particle's position, we change its state, but we do not change the global constants of nature. We do not alter the cosmological constant or the mass of the electron or the density of dark matter. Those parameters appear fixed in all the data we have. They do not drift in response to human activity. It is useful to think in terms of scales. On human scales, we are used to systems that respond. If I speak to another person, they answer. If I push a door, it opens. If I heat air, it expands. These are interactions between systems with feedback. But the universe on the largest scales is not a feedback system tuned to us. It is a dynamical system governed by differential equations. The Einstein field equations relate the curvature of spacetime to the energy and momentum content. The Friedmann equations describe how the scale factor evolves in a homogeneous and isotropic universe. When cosmologists solve these equations with the measured amounts of matter, radiation, and dark energy, they get a history of expansion that matches what we see. That history does not include any special term for observers. This does not mean we are irrelevant in every sense. Locally, we can change our environment. We can move matter around on planetary scales. We can alter atmospheres. We can send probes to other planets and maybe someday to other stars. But on cosmic scales, the energy we control is negligible. The gravitational binding energy of a galaxy or the energy content of a region of dark energy is far beyond anything we can affect. The universe's large-scale evolution is effectively decoupled from our choices. The acceleration driven by dark energy has another consequence for the apparent silence of the universe. As the expansion speeds up, distant galaxies recede faster and faster. There is a horizon, a distance beyond which light emitted now will never reach us in the future. Over very long times, more and more galaxies will cross that horizon. Their light will fade and redshift beyond detectability. The observable universe will shrink in terms of the number of galaxies we can see, even though space itself continues to expand. In a far future dominated by dark energy, observers in a typical galaxy may see only their own galaxy and a dark, empty sky. The cosmic web will still exist beyond their horizon, but it will be forever out of reach. We infer this fate by extrapolating the current behavior of dark energy. If it remains constant, the universe will approach a state called de Sitter space. The expansion will continue exponentially. Structures that are gravitationally bound, like galaxies and clusters, will remain intact, but unbound structures will be pulled apart by the expansion. The cosmic microwave background will redshift to wavelengths so long that it is practically undetectable. The universe will not end in a dramatic event. It will just become colder, emptier, and more isolated on large scales. This scenario is sometimes called the heat death or big freeze. There are other theoretical possibilities. If dark energy were to increase in strength over time, with an equation of state parameter less than -1, the expansion could become so violent that even galaxies, stars, and eventually atoms are torn apart. That is the Big Rip scenario. Current data do not demand this behavior, but they do not completely rule it out either. On the other hand, if dark energy were to decay or change sign in the distant future, the expansion could slow, stop, or even reverse, leading to a big crunch or a more complex cyclic evolution. Again, this is speculative. Observations today favor a cosmological constant and eternal acceleration, but with uncertainties that leave room for some variation. In all these scenarios, the key point is that the universe's fate is controlled by the properties of dark energy and the total matter content, not by anything like intention or response. The constants and fields that drive cosmic evolution appear to be the same everywhere we look. They do not adjust based on location, time, or the presence of life. When we say the universe does not respond, we are recognizing that its behavior is described by universal laws, not by dialogue. Even the origin of structure in the universe follows this pattern. The tiny density fluctuations that grew into galaxies and clusters were probably seeded during an early phase of rapid expansion called inflation. Quantum fluctuations in the inflaton field or in the metric itself were stretched to cosmic scales. After inflation ended, these fluctuations became the initial conditions for structure formation. Gravity amplified them. Denser regions pulled in more matter and grew. Less dense regions became voids. Dark matter played a crucial role in this growth because it started to clump earlier than ordinary matter, which was coupled to radiation. This whole process is mechanical in the best sense. It is the unfolding of equations from given initial conditions. There is no step where the universe pauses to consider anything. So where does this leave us? We live in a universe governed by general relativity and quantum field theory, filled mostly with dark matter and dark energy, expanding at an accelerating rate. We know this because of a chain of evidence. Supernovae, the cosmic microwave background, galaxy surveys, gravitational lensing, structure formation, and more. We have a model called lambda CDM that uses a cosmological constant lambda and cold dark matter CDM to describe the universe from a fraction of a second after the Big Bang to today. This model fits a huge amount of data with a small set of parameters. It is remarkably successful, but it leaves deep questions open. We do not know what dark matter is made of. We do not know why the vacuum energy has the value it does. We do not know if dark energy is truly constant or slowly changing. We do not know what happened at the very beginning before inflation, or whether that question even makes sense in our current theories. We do not know if our universe is part of a larger multiverse, with different regions having different physical constants. These are not questions about the universe's willingness to respond. They are questions about the underlying laws and initial conditions. When I look at the data and the theories, I see a universe that is consistent, predictable, and indifferent. It does not answer when we call. It does not adjust its constants when we ask. It does not react to our presence in any measurable way. It simply evolves according to the rules of spacetime, gravity, dark matter, and dark energy. Our job as scientists is to infer those rules as precisely as we can, to test them, to push them, and look for cracks that might reveal deeper layers. And there is one unresolved mystery that sits right at the center of this picture. We see dark energy acting like a cosmological constant today, but we do not know whether it is truly constant in time and space, or whether it has subtle variations that we have not yet detected. If dark energy is not exactly constant, if its strength or behavior changes over billions of years, then our predictions for the ultimate fate of the universe could be wrong. The long-term future of cosmic expansion, the horizon structure, and the final state of matter and radiation all depend on that detail. So the open question is this: is dark energy really a simple cosmological constant? Or is it something more dynamic that will change the course of the universe on timescales far beyond our own?